All right, see if that worked. Okay, so everybody hopefully can see, who is online can see my title page now. So yeah, I uploaded the presentation and actually 3 references that are somewhat related. In fact, by my three of my contributors here, Ellen McElhatton, Christoph Van Tricht, and Jen Kay, to the website. I'll also add that there's a few slides in here that I probably won't get to today when I actually talk about this. So there may be some interest in taking a look at some of the background slides, which just talk about a few of the data sets in a little bit more detail than I'm going to be talking about. So I started on this opening slide here, just sort of illustrating one of the fairly new, I would say, reconstructions that we've recently put together of the surface energy budget in the Arctic. This comes from the NASA Energy and Water Cycle study, which I'll talk about in a little more detail. And it's basically showing the annual cycle of all 6 of the surface energy components, the components related to surface energy exchange in the Arctic, which is defined in this particular study as this domain here that's in bright green in this little top-down view of the North Pole here. But what I want to talk about today is a little bit where this data set came from. Also some other data sets that we have from more maybe recent satellite products, and also how we're using those to try to understand how they relate to reanalyses and how they also can be used to evaluate climate models. So just to go on a little bit, to take a kind of a step back at where that data that I just showed comes from before I really get into the details of it. I wanted to very briefly describe this NASA Energy and Water Cycle study, and in particular this one component of the NASA Energy and Water Cycle study that's related to trying to develop our best estimates, as far as we can tell, of the various components of the atmospheric energy and water cycles, both on global scales and continental scales, and on annual scales and on monthly scales. And so what this program is basically designed to do is to kind of step away from the typical stovepipe type mission-centric science teams that NASA is really well known for, and you know, that are important in their own way, but to try to actually integrate some NASA science across different science teams and actually come up with sort of more, I guess, well, like I said, sort of integrated science, address more integrated science goals, like studying obviously the climate and in particular the climate of the Arctic. So I wanted to start with this particular image here, which is actually our global perspective from this one particular aspect of the NASA Energy Water Cycle study. This was related to coming up with the best estimates we can of both the energy and water cycle, basically coupled together sort of simultaneously. And to do this, we used the fact that this NASA Energy and Water Cycle team had expertise in all of these component fluxes, from the top of the atmosphere observations to things like the surface evaporation, so evaporative heat exchange, as well as ocean heat content estimates, which give us kind of an idea of how much energy is absorbed in the ocean surface. And so basically pooling together this expertise, and over several years, we were able to develop the sort of best estimate of the radiation and turbulent heat flux estimates from available satellite and satellite integrating data sets, and come up with, more importantly, error bars on how accurately we think each one of these fluxes is currently constrained using satellite observations. And then the next thing we did was use these error bars and these estimates of the various fluxes to actually impose, in kind of an objective way, energy balance and water cycle closure arguments on continental and on global scales. And we came up with this best estimate of the closed energy budget and water cycle, which is shown here on the, well, this is the energy budget in the blue numbers here. So you can see that adjustments have been made to some of these fluxes to allow the, for example, absorbed long wave and short wave energy in the atmosphere to balance to zero. or the outgoing long wave and short wave radiation at the top of the atmosphere to balance the incoming solar at the top of the atmosphere. So this is done using a variational technique. I don't have time to get into that right now, but the bottom line is we impose these constraints objectively, as opposed to some of these other estimates that you see here. These are other fairly recent estimates from the literature that impose the same kind of constraints, but in a more subjective way, arguing to adjust certain fluxes in certain ways based on, kind of intuition, as opposed to really based on their uncertainties. So, all right, that was a little more long-winded than I even wanted to get into. I really want to obviously zero in on the Arctic here. So as I said before, the idea of this project was to create these flux estimates, not only on the global annual cycle basis, but also on a continental scale, which is an example of which is shown here for the Arctic. So we actually have the same flux estimates that were on that diagram. These are already optimized now based on energy balance constraints. So our best estimates from observations or observation integrating, like reanalysis type data sets for the Arctic, and then also on monthly scales. And so I come back to that diagram I showed on the very first slide, which shows the annual cycle now of just the surface flux components. And so things like the surface emission here are shown in blue. The surface long wave radiation from the atmosphere is shown in yellow, and you can kind of see the other flux terms here in the legend at the bottom. And what I've done is I've actually added the Antarctica fluxes as well, just for sort of the purpose of comparison. And what I want to point out, I'm not going to spend a lot of time talking about specifically this result. I want to get into contrasting this result with reanalyses and climate models. But I do want to remind everybody, and I'm sure this is something that everybody in this community knows, that the Arctic has the strongest annual fluctuations in the net energy budget of the surface, which is shown here in the black, of any region on Earth. And so you can see that the Arctic surface actually receives a strong surplus of energy in the summertime and a strong deficit in the wintertime, and a really strong annual cycle in between. Also, if you notice, relative to Antarctica, the Arctic also has a much more asymmetric annual cycle, with sort of much more shortwave radiation, for example, absorbed in the springtime when sea ice is low than in the fall when sea ice, sorry, the other way around. Much more shortwave reflected in the springtime when sea ice is high, and much more shortwave absorbed in the fall when sea ice concentration is low. And you see that that's reflected in some of these data sets as well. So just want to basically point out this asymmetry between the two poles. Like I said, I'm sure everybody's kind of aware of this. What I want to focus on today is how well this kind of picture agrees with both reanalyses, which are traditionally used maybe for understanding the changes in the Arctic surface energy budget, and then also how well climate models kind of represent these this annual cycle. So this slide here basically compares just the four shortwave components, the downwelling shortwave radiation and the upwelling shortwave radiation reflected at the top of the atmosphere, to the downwelling shortwave radiation at the surface and upwelling shortwave radiation at the surface. And what I have on this diagram, in the dashed line, I have the data that I just showed, the National Energy and Water Cycle sort of observational based estimates. The other three solid curves here represent three of the most modern reanalyses we have: the MERA-2, so that's the NASA reanalyses, the JRA 55 reanalysis, and the ERA interim reanalysis. And so the reason I show the top of the atmosphere, I know this is meant to sort of be a talk about the surface, but I wanted to kind of show that the reanalysis actually tends to agree fairly well with observations in the top of the atmosphere fluxes. I mean, we would certainly hope that all of these data sets would agree in the downwelling shortwave radiation, and you see that they do agree very well, with just some slight differences owing to the fact that there's slightly different resolutions between these products. But the upwelling shortwave radiation at the top of the atmosphere, the kind of reflected shortwave, actually agree reasonably well between the products too. There's maybe a 20 watt per square meter or so spread right in the heart of summer. But over the course of the year, there's not too bad of a bias here between the various products at the top of the atmosphere. But when you get down to the surface, that's when you start to see some pretty big differences. Even though the reanalyses are assimilating satellite observations, you see that there's actually quite a bit of a spread between the reanalysis products, and there's some significant biases between some of the reanalyses and the observations. In particular, not to really pick on MERA, but it is the one that performs probably the least well out of the three that I'm showing. You do see that there's a significant underestimate here in the amount of shortwave radiation that makes it down to the surface in MERA relative to the observations, and also a significant, maybe for the same reason, reduction in the amount of reflected shortwave radiation from the surface. So even though MERA actually does a reasonably good job here at getting the outgoing shortwave radiation correct, that it looks like that may be due to a compensation of two errors here. One, that MERA has maybe too many clouds, which is actually reducing the amount of shortwave radiation that makes it to the ground, and maybe also some errors in the brightness of the sea ice, which allows MERA to not reflect enough shortwave radiation back to the top of the atmosphere. And so when you try to do something like look at the atmospheric energy imbalance or the surface energy imbalance, which is really what's critical for the evolution of the Arctic climate system, for melting sea ice and melting snow and on the surface, you start to see that these biases kind of lead to some fairly significant differences in estimates of the imbalances as well. So I'll start again with the top of the atmosphere, just showing that the reanalyses tend to agree fairly well with the observations. Almost all of them suggest that the Arctic has a deficit of about 1.15 petawatts of energy. So that would be the amount of energy that has to get imported from lower latitudes to sort of offset the cooling in the Arctic. But when you look at how that gets partitioned between the atmosphere and the surface, you see that the observations suggest that in all of that transport actually occurs within the atmosphere, at least in the annual mean basis, and there's almost nothing in the ocean, whereas all of the reanalyses suggest that the atmosphere or the ocean transports some heat into the Arctic region, and the MERA in particular suggests that a significant fraction of the heat transport, nearly a quarter of it, comes in from the ocean, and sort of dramatically sort of overestimates the Arctic atmospheric imbalance. So this calls into some question, I guess the ability for us to use the reanalyses for some of the purposes like tracking changes in the Arctic energy imbalance. I will sort of add the caveat though that of course there are uncertainties in the observations as well, and I did not put error bars even though we have them on on the dash curve here, and so we do need to take this with a little bit of a grain of salt, but the very fact that there's some differences here in the estimate suggests we still have some large uncertainties that kind of need to be worked through. Okay, moving on to looking at climate models then. We've done a similar analysis, and this is work that a former student of mine who's now a researcher in my group, Marion Maitling, has done, and we're getting ready to write up. This is a comparison of the NEWS estimates, the NASA Energy Water Cycle Study, versus the CMIP-5 models. And now I'm showing both downwelling and upwelling, long wave and short wave, but only at the surface. Just to give you kind of an idea of where the climate models lie on this whole spectrum. And what you see is if you compare the ensemble mean from the CMIP-5 models, that's this purple line here, where now the NEWS is shown in blue. The purple line actually agrees very well with the NEWS estimates. And so the climate models on the ensemble mean are actually doing a fairly good job at representing most of the fluxes. Although if you look at the downwelling long wave radiation, this is the amount of radiation emitted from the atmosphere to the surface, you do see that there tends to be kind of a cold bias in the models in the wintertime and a warm bias in the atmosphere and the models in the summertime. And that kind of offsets itself over the course of the year, and we get reasonably good agreement when you look at the annual mean. But the other thing I want to point out here is that when you look at the spread across models, there's still a fairly surprisingly large spread, I would say, between models. For example, if you look at the reflected shortwave radiation, even on the annual mean, there's a factor of 2 between the lowest estimate out of the CMIP-5 models and the highest estimate of the CMIP-5 models. And you can see that that's even bigger depending on what time of year you actually look at the spread. So again, we can take a look at atmospheric imbalances and surface imbalances. I won't go into a lot of detail here other than to maybe show here the imbalance at the surface in the summertime. And what we see again is that even though the ensemble mean actually captures the NASA Energy Water Cycle Study estimates very well, there's a factor of 3 spread here between the various climate models in their prediction of the surface energy import in the summertime but by the oceans in the summertime in the Arctic. And so clearly there's some value, I think, in having these observation-based estimates for evaluating what climate models are doing, and also maybe trying to examine the physics that's responsible for this spread between models. This is just another version of that Arctic imbalance slide that summarizes some of what I've been saying before. So basically, again, the main point here, now the observational estimates are in black, the ensemble means are shown in purple, and then the minimum and maximum from the model are shown in blue and red respectively. And again, you see that the ensemble means actually agree with the observations generally within the error bar of the observations in almost every case, maybe with the exception of this sensible heat here. But the spread between the models, again, is actually fairly large in some of these fluxes. For example, like the downwelling shortwave radiation here, where the spread is 40 watts per square meter between the maximum and minimum of the models. What I want to end with here is, so that hopefully sort of highlights some value to some of the satellite observations of surface energy budget that we have. I want to kind of end with one more study that we've done recently. This was by a student of mine, where we're trying to look at least one possible cause of these biases or spread between models, and that is the role of clouds in modifying the surface energy fluxes. And so for this study, we're using the CloudSat and Calypso observations of cloud location, structure, and phase, also some estimates of falling snow from CloudSat, and some radiative fluxes that are consistent with all of those cloud products that we have, and also consistent with series top of the atmosphere fluxes, which we use as an independent evaluation. So this is an example here of the data sets that we're talking about. This is the reflectivity observed by CloudSat, and this is the backscatter from Calypso. The only thing I want to point out here is that with the combination of these two measurements, we're able to estimate falling snow, where clouds exist in the atmosphere, and also go a step further and actually identify the phase of the clouds by looking at where Calypso has a really strong backscatter and where CloudSat has low reflectivity. We're able to identify mixed phase clouds for the first time, really using satellite observations. And so what we've done, oops, sorry, that slide didn't come out really very well. I'm not sure what went on there. But anyway, what we did there is we evaluated the model. We basically took a look at the CESM, now just a specific climate model, the large ensemble representation of supercooled liquid containing clouds and surface energy fluxes. I'm going to get out of presentation mode here really briefly because for some reason this didn't show up. But this is a comparison here of the fraction of clouds in CESM that contain supercooled liquid over the Greenland ice sheet, and this is the comparison against the CloudSat and Calypso observations. And one thing you should see right away, well, this is the difference between the two of them, you should see right away that there's a significant difference, significant underestimate over the entire ice sheet in the CESM model of the amount of supercooled liquid containing clouds. And so what we found, but when we looked at the fluxes, is that this directly leads to a underestimate in the amount of long wave radiation that's incident on the surface in the CESM models. So you can see here our flux estimates from CloudSat overestimate or are higher than the corresponding downwelling long wave radiation in CESM in every spot on the ice sheet. And even when you integrate over the entire ice sheet over the whole year, CESM has about 20 watts per square meter too little downwelling long wave radiation over the ice sheet. Interestingly, so this was from some work that we did with Jen Kay. Jen Kay shared this figure where she compared the surface temperatures predicted by the CESM model over the ice sheet to in situ observations, and she found that almost everywhere over the ice sheet, CESM is actually also too cold. And so maybe I should rephrase this to say not climate models, but CESM specifically. But this is kind of an interesting result that's very consistent with the fact that maybe the CESM doesn't have enough supercooled liquid containing clouds and is underestimating the downwelling long wave radiation. So we took this one step further, and that was to try to actually sort out why maybe CESM had too few supercooled liquid containing clouds. And so there was a theory based on ground-based observations in a few limited locations that it's the fact that CESM produces snow too frequently, or climate models in general produce snow too frequently, and scavenge too much of the supercool liquid containing clouds, that they don't live long enough and that they don't have enough, obviously, of a radiative effect. Well, we were able to use the satellite observations from CloudSat and Calypso to kind of demonstrate that this does hold on the entire Greenland ice sheet and actually over the entire Arctic. So these two panels here show comparison of the snow accumulation in CESM over the Arctic versus the snowfall accumulation from CloudSat. And you see there is about a 20% maybe overestimate in the snowfall over the whole Arctic in CESM relative to CloudSat. This result here, interestingly, shows sort of a corresponding result from a paper by Cyril Palerme, who did the same kind of a comparison over Antarctica and showed that almost all climate models over Antarctica produce too much snowfall over the course of a year, the annual average, than the CloudSat observations, and actually also relative to reanalyses. So this seems to be a fairly ubiquitous property of all climate models over both poles. But again, my student Ellen took this one step further and kind of combined these results and took a look at the fraction of Arctic liquid containing clouds that actually produce snow. And this is where we kind of came up with what we thought was the sort of smoking gun for what's going on here. This upper panel here, or this upper red line here, shows the fraction of Arctic liquid clouds that snow in CESM. The blue curve here shows the result from CloudSat and Calypso. And what you see is that there's about a 40% sort of discrepancy here in the frequency with which the model produces snow in Arctic liquid containing clouds versus the observations. So the observations suggest that only about 25% of the liquid clouds ought to produce snow, whereas the model produces it about 60% of the time. So not only are the observations able to kind of demonstrate that the cloud fraction is biased between the models, but it's able to also somewhat diagnose maybe the process that's responsible for doing that in much the same way that it has been done using surface observations in the past. And actually, I'm going to make one more point related to surface observations, and that is sort of to touch on maybe an idea that there's a lot of synergy here between surface observations and satellite observations. We went one step further to kind of verify that the satellite observations weren't completely out to lunch. We took advantage of the fact that there were some CloudSat observations very close to the summit station observations that were made during ice caps in Greenland. And we're actually able to produce this plot, which shows similar results that were on the previous slides, but now just for the one CloudSat and Calypso pixel that's located right over Summit, Greenland. And so what this upper panel shows is the frequency of liquid-containing clouds over Summit. The blue curve is, again, the satellite observations. The black curve is now the ground-based observations. And the red curve, which you can barely see on here, is the observations from the CESM large ensemble. And so again, you see that the two observational data sets, very independent satellite and ground-based observational data sets, agree fairly well at the frequency of liquid-containing clouds, whereas the model is way off on that estimate. Also, the downwelling long-wave radiation estimates from the satellite and from the surface observations agree very well. And you can see, again, this clear evidence of a bias in the CESM model. And when you look at the precipitation frequency, again, you get, in liquid-containing clouds, you get reasonably good agreement between the ground-based observations and the satellite, although you do see some discrepancies here starting to form, and that's due to the sensitivity of the various instruments for detecting snow. But once again, you can clearly see that the model's producing snow far too frequently in these liquid-containing clouds relative to the two observational data sets. So there's a nice synergy here, which I guess I'll promote once again on this slide here. I think there's real value to taking what we learned from ground-based observations and trying to export it to the entire Arctic using satellite observations. And so I'll conclude by just saying that satellite observations have now been used in that kind of a manner to generate new integrated assessments of the Arctic surface radiation budget and its seasonal variation, as well as cloud cover. Reanalyses are showing some fairly systematic biases relative to these observational estimates, and that does have an impact on implied oceanic and atmospheric heat transports. Also, climate models are performing fairly well in the ensemble mean, but there's an extremely large spread between the various climate models, and that may be linked to things like how clouds are parameterized or how the precipitation process is parameterized in the model. So just again, to take one model, the CESM, and this is CESM1, not the new release that's about to come out, I think, but the original CESM does appear to both overestimate a source, so it overestimates the amount of snow falling on the Greenland ice sheet, and underestimate a sink, the downwelling long wave radiation on the ice sheet, which could cause fairly significant bias in the rate of ice mass loss in the model. And I'll add one further point here, and this is again kind of coming back to modeling. This is some new work we're working on now, is if we can couple these observational estimates to ice sheet dynamical models, we can actually get some insights into exactly what the impact of various biases are on the actual specific processes that occur on the ice sheet. And so we're starting to do that now, and we're starting to find that these radiation biases are having a significant impact on the melt rate, the refreeze rate, and the runoff rate, and then in turn, the rates at which ice flow around on the ice sheet. And we're in the process of doing some sensitivity studies right now to try to quantify the impact of model biases on these various ice sheet processes. So that's all I had.
Thank you, Tristan. Is there any, does anyone have any questions on this presentation?
Ashley, this is Renee Tatusco. Do you hear me?
I do.
Hi, Tristan. I'm with the National Weather Service Alaska region. I'm just curious, this is a very fascinating study. I'm just wondering if you have compared the model and the satellite observations with the ground-based observations as part of the ISOA network. It might be interesting to see what sort of results you get from looking at the various Arctic observatories that are around the high Arctic.
Yeah, I think that's a great idea. I think the only set of sites we've compared to so far are the ones right around Greenland. So there are, I guess, maybe 10 or so sites, or maybe a little bit more than that around Greenland. And I know Christoph, in his paper, did a comparison of the fluxes and heating rate algorithm for estimating the surface fluxes from the satellite against those sites. But I don't think we've done it across the entire Arctic. So that's actually a really great suggestion.
Tristan, this is Heis. I was wondering to what extent the evaluations of the model have taken advantage of the instrument simulators, or whether those are comparing kind of raw output variables from the model.
Sorry, I'm having trouble finding the unmute and mute button here. Yeah, so actually, no, that's a really great question. What we did, so in the paper, we kind of addressed this in a couple of ways. Right now, we were unable to use simulators to actually make sure we're looking to sort of doing apples to apples comparisons, basically because there was no snowfall simulator, like no CloudSat snowfall product simulator in the CESM up until very recently. We've just sort of started building one in. But what we did was we actually used different thresholds based on what we know of, based on CloudSat reflectivities. We applied sort of different snowfall minimum detectable thresholds to the CESM output and demonstrated that the results hold somewhat independently of what you call snowing versus non-snowing clouds, and also what you consider to be a liquid containing cloud versus non-liquid containing cloud. The details are in a paper that I summarized in the references on the next slide, and actually one that I uploaded to the website. But it's an excellent point, and what we need to do is probably come back and repeat the study when we get the precipitation simulator embedded within CESM, which is now just starting to be tested. Jen K has kind of wrapped up getting the code running for that, and we do actually have a CloudSat snowfall product simulator, and of course we have a Calypso super cool liquid containing cloud simulators already in the CESM. So we should be able to come back and redo this study and make sure that the comparison is actually apples to apples. But I will say, like I said, we tried some different thresholds and the results are pretty robust, independent of what we call a snowing pixel and what we call a super cool liquid containing cloud pixel.
Okay, thanks. And not to hog the question time, but the other question I had was about the comparison between the satellite perspective and the ground-based perspective, where it looked like the satellite observations were detecting more liquid-containing clouds than the surface during certain parts of the year, and that seemed counterintuitive to me, perhaps because I would expect that some of the clouds would be close enough to the surface that the satellites would not be able to see them. So I don't know
Yeah,
if
so
you
I think you're maybe talking about this spot here. I mean, it's really just 1 month where that's
yeah, I mean,
true.
well, this looks like generally the blue band is above the gray band for parts of the year.
Yeah, I guess right here. Yeah, so I think this could be actually partly due to a sensitivity issue. So the supercooled liquid containing, or the supercooled liquid is being retrieved from these ground-based observations using the microwave radiometer, an upward pointing microwave radiometer. And that actually does also have sensitivity limitations. I think it's limited to maybe 5 grams per meter squared or so of water. There's people that know more about that. Maybe somebody like Matt Shoup or Dave Turner would probably know a little bit more, but we were given some guidance, I think it was from Dave, about the limitations of the ground-based instruments. Whereas the LiDAR, yeah, so there's the LiDAR and the radar have an issue of, if you have a very, very shallow supercooled liquid-containing layer, it's difficult to detect, but the LiDAR might actually be a little bit more sensitive than the microwave radiometer to the liquid-containing clouds. And so it is possible that it's a sensitivity difference. There's maybe some other possible explanations. I mean, maybe there's field of view issues that because the satellite observations are smeared out over a slightly larger area, we may be detecting a slightly higher fraction. It's an interesting question. I mean, obviously there's no question that the difference between the model and the observations is much larger than the difference between the observations, but it's probably worth exploring exactly why the satellite tends to see a little bit more supercooled liquid containing clouds than the ground-based sensor.